And what is in this context a restricted analytic function? This is a function which has this form here, can be described by a real power series on a hypercube of the form -1, 1 in the power of n. Otherwise, this function vanishes. So such a restricted analytic function vanishes also at infinity. And for example, if you take the global exponential function or the global sine function, restrict this onto the interval -1, 1, then it's a restricted analytic. And this is a structure which is also O-minimal. And the definable sets and functions which live in this structure are the so-called globally subanalytic ones. And important at this point is that a globally subanalytic function is polynomially bounded. So actually the global exponential function is not globally subanalytic. And so it's also not definable in this structure RIN. But of course, there are some O-minima structures where this exponential function lives. For example, the structure Rx. This is a structure generated by the graph of the global real exponential function, of course, also all semi-algebraic sets. And this is also O-minimal. And then you can combine the structure RIN with the structure Rx in order to obtain the O-minima structure RINX. This is a structure generated by all globally subanalytic sets and the graph of the global real exponential function. And RINX is a very, very important structure since a huge class of elementary functions is definable in there, like the global exponential function, the global logarithm, hyperbolic functions, the global arctangent function, or the restrictions of the global sine or cosine function on the interval -1 to 1. And also, O-minimality is also very successful regarding some applications, for example, in number theory or geometry. And the most important structures are in this context RIN and RINXP. Okay, so outgoing from these examples, I want to introduce now the notion of complexification at this point. Therefore, we fix an O-minima structure on the reals. And we say also that definable means M definable with parameters at this point. And what is now global complexification? At first, I mentioned what it means to be definable in the complex setting. So here we have to set up this map here. So we identify the complex numbers with R square via this canonical map here. And then we say that the subset set is definable. If it's also it's definable, considered as a subset of R in the power of 2m. And then we say the following. We say that this O-minima structure here has complexification if now the following holds. So if every real analytic definable function has locally a definable holomorphic extension, so take the domain of this function, take a point, and then you find for this point an open neighborhood such that the restriction of the real analytic function on this open neighborhood of this point has then an extension which is holomorphic. And very, very important at this point is that you have here also the definability, since if you would drop this requirement here on the definability, then this definition would be superfluous, since then you have such a holomorphic extension anyway, simply by power series expansion. Okay, so this is not a trivial definition. And let's look at some examples at this point. So, for example, if M here is the O-minimal expansion of RIN, so for example, RIN, RINX, or even larger O-minima structures than RINX, then this structure has complexification simply by power series expansion, since you can write a real analytic function as a convergent power series at any point. Then you can plug in at a small neighborhood in the complex numbers, also complex numbers into the power series, and then this complex power series is also RIN definable. So you see that this is then fulfilled. But important is here that you have these restricted analytic parts in the O-minima structure. Since if we go, for example, look at Rx without this AN part, then we will see, then we can show that this does not have complexification. So what is the reason for this? So the reason for this, if you give a counterexample at this point, so consider the Rx definable function, here the global exponential function. And for this Rx definable function, I can easily compute a holomorphic extension, namely this entire function here. So this entire function, so z is mapped to e in the power of z, ex cosine y plus e sine y. This function is indeed holomorphic. Okay, so you can construct such an extension, but now we have to look closer at the definability in the following way. So if we have now a real number and we have an open ball in C around this X, and now we look at this restriction of this holomorphic extension, then we see also that this restriction is a unique holomorphic extension of the restriction of F onto the intersection V with R by the identity theorem. So this is uniquely determined. And in order that this restriction here is now definable, we have that the real part and the imaginary part of this function here must be also definable, but then we need also that the cosine and the sine function restricted on a non-empty open interval is definable, but this is not the case by a result of Bianconi from the year 1997. We showed that this is not the case, that such cosine sine function, the restriction on a non-empty open interval is never Rx definable. So you see that Rx does not have complexification at all. Okay, so let's go a step further and strengthen the methods of complexification and introduce the notion of global complexification. And we say then, simply, we say then that such an O-minima structure M has global complexification if now every real analytic definable function has a definable holomorphic extension. So in this case, we find a holomorphic extension which contains the whole domain of a real analytic definable function and does not depend on any point of the domain, in contrast to the notion of complexification above. Clearly, if you, for example, drop here this requirement, definability, then this would be also a superfluous definition, since then every real analytic definable function has a holomorphic extension simply by taking the single power series at the single points, including all of them together. Note also that if a structure M has global complexification, then it has also complexification. So the consequence is that the O-minima structure Rx does not have global complexification. So here we have a counterexample. But of course, there are also some results on global complexification by my supervisor, Tobias Kaiser, from the year 2016. He's also in the audience. And he could show that the following holds. So the first one is that the O-minima structure R has global complexification. So this is a result which appeared in the archive for mathematical logic. And what is the idea to prove this? So note that if we deal here with the O-minima structure R, then we have to deal with real analytic semi-algebraic functions. And such functions are called Nash functions. And for Nash functions, there are nice descriptions like the 18-Mesa description or the implicit function theorem. And with this both descriptions, one can show this result here. And the second one is that the O-minima structure RAN has global complexification. This is a result which appeared in the Israel Journal of Mathematics. And for my research, the proof of the second statement is important for technical reasons. I want to give the proof idea for the second statement at this point. So what is the idea here for the proof of the second statement? We can write a globally subanalytic function piecewise in the following form here. So there are preparation theorems of Liu-Rollard for globally subanalytic functions. So we can write this function piecewise in this form. So take the domain of the globally subanalytic function, and then you find for this domain a definable cell decomposition such that on each of these cells we can write this in this form, where the following holds. So let me explain the single components of this preparation. We have at first that these exponents here are rational numbers. Then we have also that this a, this function, this coefficient a or this coefficient bi, these are globally subanalytic, depend only on t, and this theta depends only also on t. And this variable t, of course, can be a tuple of n variables, and this x is a single variable. And the next one is that this V is a power series which converges absolutely on an open neighborhood of this hypercube here. This power series is away from 0 and away from infinity. And we have also that the components of the power series here are contained in this interval -1, 1. And this x here is a single variable, so this is very important. And what is now the idea? To establish some results on global complexification. So take this preparation theorem here and plug in, for this x, plug in complex numbers and extend this piecewise into the complex numbers by plugging in here complex numbers for x. Okay, so this is roughly speaking the idea here. And I want to show you the idea in more detail. So if you have here this cell C, and if you have here the center theta of this preparation, then you can compute a holomorphic extension in this X in order to obtain such an orange set, which defines this, the domain of the extension. So note that you can go here a little bit outside the cell, so this with this annulus. And why can we do this? Because here we have a power series which converges absolutely on an open neighborhood of this hypercube here. And so you can extend this power series to a complex power series which converges on an on a polydisk with radius r bigger than 1. And then outgoing from this consideration, you can then extend these components suitably. You can extend this monomial here at the front suitably, and this gives then this annulus here. But note also, since you have to deal with rational powers, that you get here a slice. But this does not matter actually. And then outgoing from this consideration, the idea would be to take all the single cells, to glue the single cells together in order to get a global complexification of one variable, and then do a technical induction on the number of variables. So this is the idea, but this is not so easy at this point, since here you have a little gap around this center theta, and you have to close this gap in order to enable this induction. And therefore, you need some results on integration. And by these results, with these results on integration, you get then this red area here. And this red area, together with this orange area, gives then the desired holomorphic extension in one variable, then glue all of them together, and then you can do an induction on the number of variables here in order to obtain this result on global complexification. In the globally subanalytic case. So we have seen that the pure real field, the real field R has global complexification, Rn has global complexification. The proof ideas are quite different. So in this question, in this context, the following question arises, namely, does Rn(Exp) have global complexification? And note that there is no general method to establish such very technical questions, to give some proofs about global complexification. And this is indeed an open question in this context. And this is a question which I dealt with in my PhD thesis. And to investigate this question, I want to introduce some more notation. So further notation here. From now on, definable means Rn(Exp) definable with parameters. And We have also the notion of terms. So terms are LANX block terms, where L is the language of ordered rings. So with constant symbols 0 and 1, with the multiplication, the addition, taking reciprocals with respect to the addition, then you get this language L. And then you can take for every restricted analytic function one's function symbol into L in order to obtain the language LAN. And then take also function symbols for the global exponential logarithm into this language LAN, then you get LANX block. And for example, in this context, x squared and x of x times y squared times logarithm of z are terms. And if you can describe such functions by terms, then you see that this function has a nice form. And why is it worth speaking about such terms in the context of the O-minima structure RNX? Since there is a very deep model theoretical result of Van den Dries, McIntyre, and Marker from the year 1994, which appeared in the Annals of Mathematics, which states the following. So which gives us a precise statement how such definable functions look like. And it states that if you have a definable function, then this definable function is piecewise given by terms. So you can decompose this domain here into finitely many definable cells. And on each of these cells, we have that f is given by such a term, as I explained above. Okay, so what means this? This means that a definable function or definable functions are piecewise compositions of globally subanalytic functions, the global real logarithm and the global real exponential. And so we can also say, we can call these definable functions log-Exp analytic. And what means this? So how can we now investigate the question of global complexification in RNX outgoing from this consideration? So you can take the single terms, compute a holomorphic extension of the single terms, and then glue all of them together. This would be an idea. And basic observations in RNX in this context are the following. So if you consider the logarithm here, the logarithm has a global complexification in this way. So here the slice plane, z is mapped to a logarithm of the absolute value of z plus e argument of z. The argument is globally subanalytic, and this is also RNX definable. So the whole thing becomes RNX definable. So this is no problem. And for example, if you look at the global exponential function, you have also a global complexification in the following way. So here this x, so x plus ey is mapped on ex cosine y plus e sine y. So here we have to shrink the imaginary part in order to obtain that the cosine y and the sine y are definable. And then you get here also a definable function. But it's very important to shrink this imaginary part here, since a global cosine or the global sine function is never definable in an O-minima structure. So here we have, if you compute a holomorphic extension of the global exponential function, you get only small domains with respect to the imaginary part. Okay, and outgoing from this observation, we see that terms have a nice holomorphic extension. And with these observations or with these considerations, Tobias Kaiser could also give the following result about complexification for functions in one variable. Here we have an open set, and we have a definable real analytic function here. This has also global complexification, so a definable holomorphic extension. But note, it's very important that we deal here with only one variable. And so how to prove this? So we can describe this function f here on a dense subset of u by the terms, and then you can compute a holomorphic extension. And then we can look onto the complement of this dense subset with respect to u. And since we are in the O-minima context, we see that this complement consists only of finitely many points. But on these finitely many points, we can compute the power series expansion. Then we have also definability, and then we can glue all of them together in order to obtain this result here. So,
can I ask something?
Yes.
If you have a real analytic function, is it really possible that you will need the partition, or is it always only one piece maybe?
So if you have a real analytic function, to have in RANX, you have analytic cell decomposition.
I'm asking, do you actually need a partition, or if it's real analytic, then you will have only one piece, so it will be one composition of a sequence of function?
Yes, you have. So the starting point is that you have a real analytic function, but you need this description by the terms. And for this term-wise description, you need the partition then. Is this what you meant?
Yeah, I just meant, do you really need the partition if you have a real analytic function? But I guess you say that you have examples where you actually need a partition.
Yes, I think so, yeah. Because you
All
need, it's not in general possible that you can describe a real analytic function by one term. And the idea is to compute the holomorphic extensions term-wise, so term by term, and then you get a partition.
All right.
So in general, yes.
Thank you.
Yes. Okay. So outgoing from this consequence, so note that this method fails if you deal with more than one variables, since then you don't have control. So the then subset are in general also infinite. So what is so this is the starting point for my research. I have considered definable real analytic functions in more than one variable. So this is what I did. And so actually the same idea as Tobias Kaiser. I took also preparation. I want to look at preparation theorems for RANX definable functions, compute the extension in one variable, and then do the induction on the number of variables. But there are some differences between the structure RAN and RANX, also from the analytical point of view. The dividing line there is a dividing line which comes from the global exponential function. In the following way, I will explain this with an example. So if you look at this definable function here, so this does not have the same analytic properties as globally subanalytic functions. Since, for example, if you look at globally subanalytic functions, a globally subanalytic function is, for example, strong quasi-analytic. Or one knows also that the Tamm theorem holds for such globally subanalytic function. And this would be a counterexample for this, for example, this strong quasi-analyticity. So here we have that this function is the infinity at 0, but not real analytic, and not the zero function, and every derivative, the nth derivative vanishes at the point 0. So here you see there are some differences. And also, if we look at global complexification in more detail, if you take, for example, if you have here this exponential function, then in general, the holomorphic extension becomes too small to enable this induction on the parameter, since we have seen above that you have to shrink the imaginary part. So what is the idea at this point to avoid such features? The idea is that we identify a family of functions which goes from the point of view of definability beyond RAN, generate the structure RANX, but not from the point of analysis. Since if you look here at this function, then we get problems, for example, with strong quasi-analyticity at the point 0, where this argument of this exponential function goes unboundedly into the game. And this is exactly the idea which I had to consider restricted log-exp analytic functions. So definable functions where these arguments of the exponentials come only locally bounded into the game. And this is a class of functions I considered in my PhD thesis. But I want to introduce this class of functions formally. So here call a function now log-analytic if f is piecewise a composition of globally subanalytic functions and the global logarithm. So for example, this function here is a log-analytic function. Or you can also say that a log-analytic function, these are precisely those definable functions which are piecewise given by this terms here. So here this LAN from above, here this -1 for the reciprocal, here the nth roots, and here the logarithm. So these both notions are equivalent. And now outgoing from this notion, we can also look at restricted log-exp analytic functions. So if f is now the composition of log-analytic functions and exponentials of locally bounded functions. So what is a restricted log-exp analytic function? So for example, here, this function is not restricted log-exp analytic. Since a restricted log-exp analytic function has the same asymptotical behavior as a log-analytic one, here in the interior of sets, here also at 0. But here you see that the asymptotical behavior is the same as x of -1 over x, which is not a log-analytic function. So you see this is not restricted log-exp analytic. But if I consider here this restriction here, this restriction on r bigger than 0 is restricted log-exp analytic, since this argument here is locally bounded actually. So what do we see? We see the globally subanalytic functions are contained in the log-analytic functions, are contained in the restricted log-exp analytic functions, and this is also contained in the log-exp analytic functions, which is a class of definable functions. So this is the chain here. And now, what is my research? Here we have established some differentiability results and global complexification for the big class of restricted log-exp analytic functions. And here the strategy is the same as in the globally subanalytic case, that we have to determine a suitable preparation theorem for a restricted log-exp analytic function. Here further notation, T range over Rn, x over r, and then here we have the projection on the first n coordinates. And what is then, so I want to start with the preparation theorem for log-analytic function. So here we have a definable function, so we need a definable set. We need the following technical tool, which is called logarithmic scale on C, with such a center theta, to describe the iterations of the logarithm. And we call such a tuple logarithmic scale if the following holds. So yj is bigger than 0 or yj smaller than 0. Then theta j of t is a definable function of p of this on this set here. Then we have also that y0 of tx is x minus theta 0 of t. And we have that yj of tx is the logarithm of the absolute value of yj minus 1 of tx minus theta j of t. And here you see, for example, this j here describes that the j times iteration of the natural or of the real logarithm. And with this technical tool, we can describe also, so I can define a log-analytically prepared function, and we say that a function g is log-analytically prepared if it's of the following form. So here, similarly as in the globally subanalytic case, here the difference is that we have to deal with an R logarithmic scale in general, which is of length R and at length 0, where the following holds. So Qj, Pij's are rationals, and we have that these coefficients here, these are also definable functions on P of C. So this depends only also on T. T can be also a tuple of n variables. And we have then that this y0 to yr is a logarithmic scale on C. Then we have also that with a power series which converges on the open neighborhood of this hypercube here, away from 0, away from infinity. And we have also that these components here are contained in this hypercube. Okay.
Are they all real analytic, or you don't assume that?
What?
Are the functions all real analytic, or you don't need that? They're just
I don't need that, no. No, the original function is real analytic in the theorem, but these functions are not real analytic in general. So I don't need this. But since with the preparation theorem below, we can assume that they are real analytic, because you have analytic cell decomposition in R and X. So you can assume this then, but I don't need this actually for later on. Okay. Then, so this is a log analytically prepared function. And then outgoing from this preparation theorem, there is a version of Liu-Rollin from the year 1998, and it states the following. So here we have a log-analytic function, and then we find a partition C of x into finitely many definable cells, such that the restriction of the function f onto C is then log-analytically prepared for every C in C. So this is the preparation theorem of Liu-Rollard. And in general, even if you have here a log-analytic function, the underlying function is log-analytic, then this function f is in general not log-analytically prepared with log-analytic data, since here we see that A, B1 to Bs are in general definable functions. There is no statement which, if these functions here are log-analytic, or the center of the logarithmic scale is also only definable, but not log-analytic. And I could give also a counterexample in my PhD thesis to show that this cannot happen in this way. So this is this, but you can show that this A, this coefficient A is the B1 to Bs, then the center theta, these are compositions of log-analytic functions and exponentials, which comes from another logarithmic scale on C in general. So this is, if you go through the proof of Liu-Rollard, of Van den Ries and Speisecker, so there the preparation theorems originated, you can show this then. And this is the reason why I introduced the notion here of C here. So what is a C here? A C here is a function which is given by exp of theta L tilde, where this theta L tilde here comes from this logarithmic scale here with center theta 0 tilde or theta r tilde. Okay, so this is C here. We call then a function C nice if G is then the composition of such log-analytic functions and C hairs. And important point here in the connection of in this context is that a C nice function is actually restricted log-exp analytic, since one can also show that you have control on the center of a logarithmic scale in general, and you can show if the underlying set here is open, that the underlying cell is open, that the center of every logarithmic scale on C, this is also locally bounded. So you have also strong estimations which determine the center of a logarithmic scale. And outgoing from this preparation theorem, or outgoing from these considerations, I could prove in my PhD thesis the following result. Here we have a log-analytic function, and a log-analytic function, then I find a partition C of x into finitely many definable cells, such that the restriction on C, this is log-analytically prepared with C nice data for C in C. So this means that you have here this coefficient, these base functions here for the center theta of this logarithmic scale. These are C nice, as I defined above. Outgoing from this preparation theorem, I could also give a preparation theorem for log-exp analytic function. So here we have, there is a preparation theorem. So we say then that this function f here is log-exp analytically prepared. Now the following holds. So here we have the same setting as above, with the difference that here we have these exponentials. So this is the additional thing that we get here, these exponentials. And here we have also that this, so we have here that this exponents Q0 to QR, these Pij, these are rationals. We have also that A, B1 to Bs are C nice functions. So here we have we are more precise now, can be more precise. So y0 to yr is in a logarithmic scale on C with such a C nice center. And we have also that V is a power series which converges on such an open neighborhood. And we have also the components are contained in -1, 1. And we have also that these functions here are log-exp analytically prepared of lower complexities than f. So this means that they have also the same form as f here. So with different coefficients, which different functions here, the logarithmic scale keeps the same. And here we have also these exponents, but they can differ from these exponents which are here. And also with exponents which lower complexity and so on. And you can, for example, say that a log-exp analytically prepared function of complexity 0 is 0. So this is log-exp analytically prepared. And I could give the following version for preparation theorem of restricted log-exp analytic functions here. So here we have a restricted log-exp analytic function, and we find a partition C of x in finitely many definable cells, such that the restriction is prepared with exponentials of functions which are now also locally bounded with respect to x for every c in C. So this means the following: we have the same conditions here as above, but here we have also that ct1 to ds, these are restrictions of locally bounded functions on x, since we plug in, so restricted log-exp analytic functions are compositions of log-analytic functions, locally bounded functions, and then if you deal with locally bounded functions, you get here also functions which are locally bounded, so this c and di. So this is the preparation theorem I could give for restricted log-exp analytic functions. And what are the consequences now? The first consequence is Tamm's theorem. So if you have an open definable set, then I could show the following. So we have a restricted log-exp analytic function, and then we find a natural number such that now for every t in Rn, so this function here, so t is fixed and x, so this is n times continuous differentiable at x, then this function is then real analytic at x. So this means that there is no gap between Cn being Cn and being real analytic. So this is as in the globally subanalytic case. And of course, this n here depends also on the restricted log-exp analytic function. And an example here would be that the Tamm's theorem does not hold in Rn(exp) in general. Consider this function here. So e in the power of -1/x, as we've seen above. Then we see that f is infinitely often continuously differentiable at 0, but actually not real analytic. So this is a counterexample for this theorem here above. And of course, consequence is that the following corollary holds. So if we have a restricted log-exp analytic function, then the set of all tx in x such that this function here is real analytic at x. This is also definable because the property of being n times continuously differentiable is also definable. And note also that this does not hold for definable functions in general. And I will briefly give you at this point also a counterexample. So if you look at this function here, so this is a definable function, but you can show that this is not that. If you look at the outpoint such that this function in x is real analytic or C infinity at 0, this is a set of integers. And this is not a definable set. Okay, so here you can also write this function as x in the power of the logarithm of x and so on. Then you see that this cannot happen, and this function is also not restricted log-exp analytic. Okay, and the second consequence is then the result on global complexification. So we have a real analytic restricted log-exp analytic function, and then f has a global complexification, which is again restricted log-exp analytic. And for the ideas of the proof is, so do the same procedure as in the globally subanalytic case. So use a preparation theorem for restricted log-exp analytic functions from above. And then we have also the following. So here we have, for example, the cell C, and here we have the case that the logarithmic scale does only depend on one component or consists of one component, and then compute the holomorphic extension. Then it's a much more complicated set as in the globally subanalytic case. Here you have not an annulus, in general, a more complicated set. Here you have also the slice, and here you have also the gap, which you have to fill by results on integration. But note that you have to determine a suitable domain of the for integration. So I plug in an annulus in order to enable this integration, and then outgoing from then there is also a result on integration. fill in these gaps here. Important is that doing some integration in the Rn-Exp case is much more complicated than in the Rn case. And then here the same idea, glue the single holomorphic extensions of the single cells together, and then do the induction on the number of variables. Important here is you see that the component of the logarithmic, that there are more than one component of the center of the logarithmic scale in general. So here you can have two such points. Then you have to consider this holomorphic extension. You get, for example, this holomorphic extension. Then you have to plug in two annuli, and then you have to do integration in more than one case. Okay, so this is the idea to get this global complexification, but note that this is much more technical. Note that this is much more difficult as in the globally subanalytic case. So it took me a very long time to write the proof for all this stuff. And so, but this is roughly the idea. And at the end of the talk, I will give you some open questions which arise in this context. So the first question would be, does a real analytic log-analytic function have a global complexity which is again log-analytic? We know that you can construct it in this way, that it's restricted log-exp analytic, but what about the log-analytic case? And if you look at the simple LAN terms or the simple terms which define such a log-analytic function, then such a log-analytic function extends piecewise to a holomorphic log-analytic function, but this is not enough. One needs also a preparation theorem for log-analytic functions with log-analytic data only. And the second question is, and this question is also pretty unsolved at present, and the second question is every real analytic definable function restricted log-exp analytic? And this may be true outgoing from the following observation. If you look again at our standard example in the following way, so here, then we see that f is flat at 0, but not the 0 function. So this feature cannot occur in the case that a real, so if this function here would be real analytic, then it would coincide with the 0 function, which is not the case here, but it's flat. So this feature cannot occur in the case of real analytic functions. And so I conjecture that this happens also if you consider the compositions. So that consider definable functions as compositions of log-analytic functions and exponentials, but it's not so easy to prove since real analyticity is a local property. But to make some statements about the terms which occur in such a function, this is a global property. And so this is indeed an interesting question in this context. And yes, so now I'm at the end of the talk, and I say thank you for listening. Thank you for your attention. And now I have an open ear for questions. Thank you very much.
Thank you very much for the very nice talk. Yes, are there any questions?
Yes, I may have a question.
Okay.
Do you hear me, Andre?
Yes.
Yeah. Okay. So at some point of your proof, you said that in order to fill the gap in the complex cells, in order to fill the gap, you use some integration techniques.
Mm-hmm.
So you've been a bit fast about that. What do you have in mind exactly? Like these? What kind of integration techniques do you use?
Okay. So here.
Yeah, for example. Yeah.
For example, here, okay, here. So here you have this gap here. And you have, for example, so what I have to do, I have to define a parameterized integral about a path here in this orange area.
Yeah.
Okay, so, and if the underlying function, so imagine that there is the set x here, for example, and this underlying function is real analytic. Okay, and then this 0 goes to this center theta goes to the cell C, then you have also that this area here is overlapped by this by the domain of the where you can express the function by a convergent power series. And the parameterized integral is defined in this way, that if this is the case, then with Cauchy's integral formula, you obtain then definability, or you can then construct here a holomorphic extension. So the point here is use Cauchy's integral formula.
Okay. Okay.
So, so this is quite technical, but so the parameterized integral has the same form as the Cauchy's integral if the underlying function would be holomorphic, and then you get definability, then you have to investigate definability. And then the next step would be that if you can here construct a natural holomorphic extension, then this Cauchy integral formula coincides then, and then you can fill in this gap here, then you get holomorphicity.
Okay.
So this is a technical point here.
Okay. Okay. Thank you. Thank you.
You're welcome.
But if I may, I may have another question, if I may. Yeah. So, where does this strange shape of the cell come from exactly?
This here?
Yeah.
Okay, this comes from, since if you have, for example, the unit. So you have to, if I look at we can go a little bit back here, maybe. If you have here this form.
Okay.
So here you have to, of course, you can compute the holomorphic extension of this V here. So this is a complex power series, no problem. And then you have to compute the extension of these components in this way that you come into this polydisk of this holomorphic extension of which defines the complex power series V. And in order to enable this, you get, in the globally subanalytic case, you get an annulus, but here this is much more complicated since you have here also functions. So these exponentials, I was, I think, a little bit fast, but these exponentials here depend also on the last variable, so on x, and then you have to compute the holomorphic extension also for this di, and then you have to do this estimation then by a positive real number, which defines the polydisk for this function here. Then you get not an annulus in general, but a more complicated set.
Okay.
And this is only, so this is in general, it's only an example below to show that this is not an annulus in general. So it can be much more complicated, but the point is, of course, that the set is definable.
Okay, yeah. Okay, very clear. Thank you.
You're welcome.
Can I ask something?
Yes, go ahead, please.
Yes.
My question actually is about also the previous result of Tobias and your results. And is there any version of this which is true uniformly? So even starting from the semi-algebraic, globally subanalytic, and if you have a definable family in some sense, given in some nice definable setting, do you have uniformly the complexification?
So of course, what I have is for this a version of, so for a family of functions, yes. So actually the idea is, if I establish global complexification, then maybe I go to where I have formulated this here. Then the idea is to do induction on the number of parameters, and then you have to deal also with parametric functions. So what I have done is I have here a variable. So in general, you have a variable t, which is fixed, and then you can compute the holomorphic extension in the last variable, for example. Then in the parametric setting, I have some results of this. But what do you mean then with uniform?
So in R sub n, let's say in R sub n, if you have a definable family of real analytic functions, can you uniformly complexify them?
I think so if this n is finite, yes, but I'm not so sure. If it's infinite.
What is n? What do you mean n is finite?
Then, so if I have n functions, and this n is finite. Then I can, of course, do a.
No, I'm asking if you have f sub t, and each f sub t is real analytic. Each one of them has a definable complexification. Do you have uniformly the complexification?
So we have it for families.
Isn't the question here that once you have a global definable complexification in several variables, doesn't that give you automatically a definable complexification?
Only if the parametrization is real analytic, right? If the parametrization is not real analytic, then it's not clear, right? It's
right. If the entire family of maps is itself a real analytic map, yes.
Right. Then of course, yes.
No, but the results holds for families.
It does hold for families.
Yes, it does.
For what kind of families?
Definable families, and each functional family has to be real analytic.
And uniformly so?
Yes.
So piecewise, the same formula defines the complexification?
Yes.
Oh, okay.
Thanks.
Any other questions?
Well, I have a much simpler question. Just to get some intuition, what is a nice, if you complexify e to the power -1 over x, where x is greater than 0. So how does the region of the complexification, definable complexification, look like? I suppose it must have some kind of cusp at 0, or?
Yes, so the point is that you have to bound here the imaginary part. So in order to, so of course you cannot complexify this function here because it's not on the whole domain, since it's not real analytic at 0. So
right,
what we can complexify is only for bigger, so for x bigger than 0, and then the imaginary part is of course then you're is then bounded by bounded by pi, for example, and then the imaginary part becomes, if you go to 0, becomes then also 0. So, and if x becomes larger, then the imaginary part can be, there's no. But important here is that the imaginary part becomes 0 if you compute the complexification of this function of this e in the power of 1 over x if x goes to 0. Then the imaginary part goes to also to 0. But note that this function is not real analytic.
Yeah, I was restricting the function to positive x. Anyway,
Yes.
Thanks.
Yes. And here the reason is you have the unbounded part of the -1 over x is not bounded at x is 0. Okay. So
okay. Any other questions in the audience?
Just to remark that maybe this last question about complexification of e to the power -1 over x for x positive is something that maybe you are going to find in any saddle node differential equation. I mean, because yeah, that is well, it's something that remains to me that you have this kind of phenomena. For instance, you take a vector field, a holomorphic vector field in dimension 2, with which is of saddle node type, and then solutions are in sectors are complexifications of this kind of functions, but in other sectors are like hyperbolic behavior or something like that. So maybe, yeah, It's a quite common phenomena, I suppose. It's only a remark. It's not a question.
Are these definable in RNX? I don't think so.
No, but not at the oh.
Yeah, I don't think so. That's the point here is right that you have the extensions of e to the minus 1 over x that are definable. The domain is much smaller than a sector.
Yeah, maybe you have to work in not in R&ESP in the station of created by real solutions of, for instance, Euler solutions or something like that. Okay, well, sorry, it was just something I was thinking, not very specific question. I'm sorry.
No.
All right. Well, thank you very much. I think we need to stop here because we have a question session coming up for Daniel's lectures.
Okay.
So, Andre, thank you very much.
Yeah, you're welcome. Thank you for the invitation.
You're welcome.
Thank you. Nice lecture.
Bye.
Thank you. Bye.